It's a pleasure to be here and give this talk on behalf of Keith. Keith's done a wonderful job over the last several weeks of showcasing to you guys the different types of problems that we can solve by using astroparticles and what we can learn about the universe around us. And so today, specifically, I'm going to be talking to you about how astroparticles impact the evolution of the moon and then how we can even use them for searching for water on a moon. And so we start by just looking at the moon of what we see every night when we look up at the sky, which is a picture of the moon in the visible light, right? And so immediately with our eyes, we can notice there's two distinct regions. We have these darker regions, which are known as the lunar mare, and these are actually basalt plains from lava flow that broke out from under the surface and eventually just dried onto the surface. And then these lighter regions are known as the lunar highlands. They're much higher in altitude. They're mountainous regions. They're much older, right? And so this is the type of information we get just by looking at it with our eyes. Now, this is an image Keith has showed in many lectures, right? And just to rehash it here, and it'll come up multiple times, light exists on a whole spectrum, right? Down at the lowest energy or the longest wavelengths, we have radio waves. And then up at the highest energies, we have gamma rays. Right? And so as we move up and down this spectrum, we can see what the moon looks like at different wavelengths of light and see what we can learn from it. So starting at the highest energy, you may remember this image from a previous lecture from Keith, but this is what the moon looks like in gamma rays. And one thing we get from this is that it actually shines brighter than the sun does in gamma rays, right? And so we have to ask, well, why is this? What is different about the moon? Because the moon's not shining off all this energy like we see in the sun. And one has to do with potentially magnetic fields, right? The sun has a very strong magnetic field, and so external cosmic rays get deflected. But the moon lacks a magnetic field, and so cosmic rays of all energies are just immediately bombarding into the surface, causing interactions, and then gamma rays can be emitted. And so as a result, the moon shines brighter. And then we can move down this spectrum past the visible and into infrared. And the infrared will give us information about the temperature profile across the moon. And so, similar to Earth, what we'd see is near the equator, it's a lot hotter, and as we go closer to the poles, it gets a lot colder, with some bright spots that are very, very warm on the moon, and these are associated with very young craters that have very large amounts of rocks in them, because rocks are much more efficient at holding on to heat. Now, the moon has very extreme temperature differences. At the coldest we've ever measured, we're at negative 416 degrees Fahrenheit, whereas at the hottest, we're at positive 260 degrees Fahrenheit. This is almost a 650-degree difference from the coldest and the warmest temperature we've measured on the moon. For reference, on Earth, the coldest was negative 129, and the hottest is 134. So that 650-degree difference that we see on the moon, on Earth, we're only seeing a 200-degree difference, right? And so we have to ask these types of questions because we want to understand the differences between the Earth and the moon. Because in terms of our galaxy, our solar system, the moon and the Earth are basically in the same place, right? And so trying to understand why the Earth has so much water, and yet when we look at the moon, we don't immediately see it, helps us to understand the differences of how different planetary environments could potentially hold water or what keeps them from having any at all, right? And so we can start by listing some differences, and one of the first ones is that about atmosphere. Earth has an atmosphere, whereas the moon doesn't. And so what does this do? Well, Keith has talked about what happened? Continuing on, the moon doesn't have an atmosphere, right? And so on Earth, cosmic rays interact in that atmosphere and distribute energy across billions and billions of particles before they ever reach the surface. Without an atmosphere, these particles go directly into the lunar surface, and so there's much higher energy in these cosmic rays the moment they hit the rocks on the surface. Now the clicker isn't seeming to go. All right. Let's do this. All right, hopefully that's the end of our difficulties, but bear with me. So the next one is about magnetic field, which I've already mentioned, right? The moon lacks a magnetic field, and on Earth, this acts as an additional layer of protection where low-energy cosmic rays will be deflected away from the Earth because of our magnetic field. Without the magnetic field, even low-energy cosmic rays are able to directly impact the moon, right? Another one is rotation. The moon rotates at the same rate at which it orbits around the Earth, right, on this time scale of a month, which is part of the reason why the moon is tidal locked and we constantly see the same face of the moon, right? And so as a result, any particular point on the moon, a day essentially lasts 2 weeks, right? You're seeing the sun for a whole 2 weeks, which contributes to why we see such high temperatures on the lunar surface as opposed to Earth. And then we get to the main question of today. Well, what about water, right? Earth is 70% of its surface is covered in water, and yet when we look at the moon, we don't immediately see any. Obviously, I've named a number of differences, but what do these differences have to do with the stability of water and whether water could be found on the moon, right? And this can then even go into a more deeper question about how life could be found throughout the universe. As far as we're aware, water is a necessary resource for life to exist. And so if we can find water in very extreme environments, does that mean life could potentially exist in extreme environments as well, right? And as for similarities, well, they're round, right? And for the purpose of this discussion, that's about where this ends, right? And so we can talk about viewing cosmic rays from Earth. And so as I stated, because we have an atmosphere, these cosmic rays interact in the atmosphere, producing a shower. And this makes them extremely hard to directly see, right? Because we're never seeing the cosmic ray itself at the surface. We're seeing byproducts of it. And so if we want to see the cosmic rays directly, we have to fly balloons or satellites and go high up into the air in order to have an opportunity to see them. And so we've done this with cloud chambers, right? Keith has shown an image similar to this, where what we did is we have these chambers full of gas, and as the particles pass through, they leave behind an ionization trail. And looking at the trails left behind, we can understand the mass of the particle, its charge, and other characteristics. And you might say, okay, can we do something similar, or do we see something similar on the moon? Well, actually, yeah, we do. When we went into the moon during the Apollo era, and we brought back samples and we started analyzing them, we saw these tracks up here, right? And what this is associated with is cosmic rays interacting and leaving behind tracks, but instead of interacting in a gas and then the gas eventually just diffuses and the track disappears, the rocks are holding the cosmic ray bombardment history over millions and millions of years. And so that's why the number of tracks is so dense, and you can barely tell where one track starts and where one ends. Let's see. Over here, yeah, there we go. You see these blobs. Those are also associated with cosmic rays, whereas instead of tracks, these are actually due to cosmogenic materials being formed in the regolith. And what I mean by that is when you have these ultra-high energy cosmic rays and they hit some atom in the lunar regolith, they're going to change the atomic structure and form new elements, right? And so these come in the form of radioactive material that doesn't naturally occur on the moon, so we call them cosmogenic. And these tracks and blobs are part of a series of processes that we call space weathering, which all works together to evolve the moon over time. And this has physical effects that we can even see by eye. So these pictures are actually 2 images of Apollo samples that I've gotten to work with as part of my thesis work. And what you'll notice is that the sample on this bottom, ever so slightly, appears as a darker color than the top one. And this is because the sample on the bottom has more tracks, more of these blobs. It's been exposed to more cosmic rays, which changes the color that you see with your eye, as well as a number of other characteristics about the soil itself, right? And so all of this is to say the moon and the Earth have very different planetary environments, right? But we are still interested in wondering what are the extreme environments in which water can exist. And the moon provides a very unique opportunity in the fact that it's close and a very different environment to study and understand how water can exist in other places, right? And so for that, we start to talk about the real dark side of the moon, or permanently shadowed regions. We call these PSRs, and these are regions of the moon that never receive any sunlight. As a result of this, they're extremely cold. They're constantly at less than negative 315 degrees Fahrenheit, right? And remember, the coldest temperature on Earth we ever recorded was negative 129 degrees Fahrenheit. These permanently shadowed regions cover about 5% of the South Pole, and there's a roughly an equivalent amount at the North Pole as well. Now, this equates to about 16,000 square kilometers or 6,200 square miles. This is about 27 Chicagos, right? And models of how we think ice should be distributed on the moon tell us that there should be gigatons of ice in these permanently shadowed regions. And for reference, gigatons of ice is equivalent to about Lake Michigan, right? And so we're talking about a potential Lake Michigan's worth of ice that we would expect to exist on the moon. We just need to find it, right? But the history of water is very interesting and how we got to this idea of there should be gigaton deposits, right? And it starts in the 1950s where we take all of our information that we know about the moon and we do an analysis. We say, okay, could water exist for billions of years? And we answer, no. There's no way water could exist for billions of years, right? It just doesn't have the right temperature and environmental characteristics for water to be stable. This changes a little bit in the 1960s when the idea of permanently shadowed regions become more popular. We reanalyze the environment of the moon with this new idea of, well, what if an area never saw the sun? And what we conclude is, well, these regions could actually have water, but do they? Right? And so then in the late 60s and into the 70s, we enter the Apollo era, where we go and we bring samples back. Now, none of the Apollo missions went to a permanently shadowed region, but the idea still being, if PSRs are capable of holding water for billions and billions of years, elsewhere on the moon, you still might expect to find small trace amounts of water. Unfortunately, all analysis of the Apollo samples found that there was no water on the moon. And this isn't to say that they found zero water molecules. In fact, what happened was any water molecules they may have found, they couldn't be confident that what they saw wasn't a contamination from bringing them back to Earth, right? And so the conclusion was there's likely not water, right? Because there's just not enough to even tell behind our background. This continues to be the idea into the 1990s that there's no water on the moon. And then this changes in 1992 when we find evidence of ice on Mercury, right? And now what does Mercury have to do with the moon? Well, again, this has to do with planetary environments. Mercury, being the closest planet to the sun, experiences very high temperatures. It has no atmosphere, and so it's also bombarded by cosmic rays directly at its surface. It has a very, very weak magnetic field, and so it does have some protection, but not a lot. And it also has permanently shadowed regions, which is exactly where we found these ice deposits, right? And so we say, okay, if an extreme environment like Mercury can have ice, why doesn't our moon? So we performed the same experiment on our own moon, looking at the permanently shadowed regions, and we say, well, maybe I'm seeing ice, right? But we're not entirely sure. It's not as clear-cut as what we saw on Mercury. A reanalysis of this same data set says, no, we got fooled. Those are actually rocks, right? And so now we're confused. Are we looking at ice? Are we looking at rocks? What are we looking at? And then in 1998, we say, okay, we can't use our typical techniques. Let's use cosmic rays. And specifically, let's look at the neutrons that come out from cosmic ray interactions. And so neutron spectrometers, what they measure is they're very sensitive to hydrogen. And here's an image of a water molecule where a water molecule is 2 hydrogens and 1 oxygen. And so if neutrons are very sensitive to hydrogen and you happen to have water, you're going to be able to see these water molecules. And what we notice is that there is an excess of hydrogen at the lunar poles, which is where we expected the water to be with. Now, this is evidence that there's hydrogen, not necessarily that it's in a water form, right? And then in 2009 and 2010, we actually do it. We discover water on the moon. In 2009, in the form of very thin frost on the surface at the poles. And then in 2010, we detected a little bit more water through an ejecta crater, which I'll talk about in the next few slides. But to understand how we discovered water, I want to talk about spectral lines. So Keith in previous talks had talked about how if you have an object like the sun with some temperature, it emits light at a continuous spectrum. So it's emitting all wavelengths, right? And so if you take an instrument and you just stare at the sun, you're going to see some spectrum that looks like that. Now, if you pass that light through a cloud of material, that material is going to absorb certain wavelengths. And so when you view the sun through that cloud of gas, you expect to see the spectrum of the sun with lines removed from it, right? And these lines give us information about the material that was inside the cloud of gas, right? And in fact, spectral lines are the fingerprints of material. All materials have unique spectral lines that they will remove from the electromagnetic spectrum. And so from this, we can back out water being in a cloud of gas, right? You say, okay, but how do we do that? By definition, the water's in the PSRs, which never see sunlight, so that doesn't really matter. And we say, okay, we need to get the material out of the PSR. So what's the easiest way to do that with minimal effort? We crash a rocket into it and we blow it up, right? And so this is exactly what we did. We said, this is a very low cost and efficient way of doing it. And we take a 40-foot long, 5,000-pound rocket, and we just send it into the moon at 5,600 miles an hour, right? This is going to be plenty enough energy to just shoot material up into the air. And then we can just view that material we can view the sun through that cloud of material that shot up. And when we do this, we saw about 341 pounds of water, or about 40 gallons of water at room temperature and pressure, right? But this is not sustainable, because the question was, well, is there water there? And after blowing it up, the question still is, well, is there any more water there, right? And then we can answer or ask new questions of, we found water, is it distributed across all PSRs? Did we get lucky? If it's there, how is it getting there? How is it being replenished, right? And so for that, we talk about the lunar water cycle, where we come up with models for how does water actually get onto the moon, right? And it can get there through a series of processes, but the most common ones are you have asteroids or comets that just have big chunks of ice and they crash into the moon and just emplace water there. But that only gives you information about how water can get to a specific area. About replenishment, the main model has to do with solar implantation, which comes from right here, in which the solar wind is actually giving us a source of hydrogen all the time, and it's implanting itself into the lunar regolith and forming water, right? And so I can talk about that a little more in depth. Remember, the moon doesn't have a magnetic field, so it's not protected from the solar wind like we are. So the solar wind, which is mostly hydrogen, which remember is 2/3 of the recipe for water, comes in and it hits the moon, as well as solar energetic particles or cosmic rays, right? And these low energy cosmic rays will get trapped in the moon. And then we say, okay, so now the moon has this excess of hydrogen everywhere, or at least it has a source. Well, what about the oxygen? Well, most of the natural material on the moon is in the form of metal oxides. So that's some metal bonded to an oxygen. So actually a lot of the moon is rust, it's iron oxide, or aluminum oxide, right? Or titanium oxide. And so the oxygen is there natively, and the sun provides us the hydrogen. And because there's little protection, high energy cosmic rays are capable of breaking these bonds. Remember, we saw these blotches of materials from cosmic rays causing spallation in the material. And so that provides opportunity for these implanted hydrogens to rebond with the oxygen and form water. Right? But what about ice stability? What makes the PSR specifically the safe haven of water? And I've alluded to this already, and it's simply that they're cold, right? Remember, less than negative 315 degrees, right? And what does temperature have to do with anything, right? Because if you think about it, if I take water at room temperature on Earth and I lift it up into space, that cup of water is going to evaporate away, right, due to the low pressure. If I want to compensate for that and try and keep my cup of water stable, I have to start lowering the temperature to compensate for the low pressure. And so we say water is stable on the moon if that region is at temperatures less than about 315 degrees Fahrenheit. That typically is our cutoff. At this rate, the rate at which water evaporates is 1 molecule per square centimeter per hour. And so remember at the beginning I said models are telling us that there's possibly Lake Michigan's worth of ice in the permanently shadowed regions. At this evaporation rate, that means over 1 billion years, we would expect 2 cups of water to have evaporated out of Lake Michigan, right? And so this is extremely stable. And so now we have this mechanism for hydrogen to get to the moon, bonding with oxygen, forming water, replenishing this water in permanently shadowed regions, and we know that these areas can hold water for billions of years, right? But how do we measure it? Because remember I said it was very difficult to find using our typical techniques, and we don't want to blow it all up. So the first one we think of is neutrons, right? And so to understand neutron spectroscopy, I have to talk about just conservation of momentum. So in a collision between two objects, your momentum's conserved. And the most efficient way to conserve momentum and transfer energy is to have the particles be the same mass. And so we look at water and we say, I want something that's really sensitive to water. Well, water is 2/3 hydrogen, so most of it is hydrogen. What has the same mass as hydrogen? Well, neutrons do. And I know neutrons are being produced all the time from cosmic ray interactions, right? Now, most collisions are not going to be head-on collisions where they transfer all their energy. If you think of playing pool, right, the two balls have the same mass. And so when you hit one, most of the time you don't hit it exactly, and they kind of go off in these glancing-like collisions. And so you might see something more like this, where the neutrons, which are those red dots, hit water molecules, and they disperse their energy throughout that system. But overall, the neutrons get trapped in that system. This is the same idea used for water in nuclear reactors, right? Water is not just used as a coolant for nuclear reactors, because these fuel rods are emitting high-energy neutrons at the level of 1 mega electron volt. But the most efficient energy for these neutrons to be to sustain the chain reaction, because we need these neutrons to hit neighboring fuel rods to keep the chain reaction going, we want them to be at 1 electron volt of energy. So we need some way to get neutrons to lose a factor of 1,000,000 of their energy before they hit the neighboring fuel rod. Well, we just said the most efficient way to take energy away from something is to surround it with an object of the same mass. So we surround it with water, and in that state, it takes about 15 collisions to take a factor of 1,000,000 away from these neutrons, right? And so this is why we say water is an efficient neutron moderator, and we surround our fuel rods with it. And so if you ever look at pictures of nuclear reactors, you'll notice they're always submerged in water. And this isn't just to keep the temperature down. It has a very physical process of actually getting the neutrons to be at the right energy to keep this reaction going. And so as we move to the moon, we can ask questions of, all right, cosmic rays are producing these neutrons. What can I do with them? Well, typically on the moon, right, from the Apollo missions, we saw there was very little water. And so a cosmic ray will come in, interact, produce a neutron, that neutron leaves the surface, and then I can just count it, right? If I have an instrument on an orbiter, I just count the number of neutrons coming out from the lunar surface. And then I hit a permanently shadowed region, which might or may not have water, but if it does, the water is going to be really good at stopping the neutrons. And so that neutron that comes out of that cosmic ray reaction gets stuck in the water. And so all of a sudden, as I go over an area with potential water, I expect my number of neutrons to go down, right? And so this is the idea behind neutron spectrometers. And so we've flown 2 neutron spectrometers, the first one being in 1998, which was the Lunar Prospector neutron spectrometer. And what you'll see from this plot is a function, or what the neutron flux looked like leaking out of the surface as a function of latitude. And you'll notice the number of neutrons coming out from the surface was roughly constant across the whole moon, except for 2 regions, the North and the South Pole, right? And so from this we say, well, we know on Earth that one of the most efficient way to stop neutrons is for there to be hydrogen. We're expecting there to be water at these regions. And so we have evidence now that says it's not conclusive that this is water, but there is water-like material there. We flew a second one called the Lunar Exploration Neutron Detector on the Lunar Reconnaissance Orbiter in 2010, which got us a much finer map of what the neutron suppression looked like at the poles. And so here is a map of the South Pole specifically, where you can see as I come in closer to the pole, the number of neutrons is going down. And it's very hard to see, but these little black rings are permanently shadowed regions, which is where we expect the water to be, right? And so we see there's a few craters or a few permanently shadowed regions where there's a lot of neutron suppression, right? And so this is indicative that there is potentially large amounts of water there, but this isn't the Lake Michigans that I promised you earlier in the talk. And part of this has to do with the fact that this neutron spectrometry technique is limited to the first meter, right? And so we must conclude, all right, maybe there's water deeper down, but why isn't there water right at the surface, right? If it's not at the surface, why would I expect it to be deeper down? And for that, we have to understand this concept called gardening. Now, Keith told me I had to put Arthur Compton somewhere in this lecture, So there's Arthur Compton right next to the crater we named after him called Compton Crater, right? And we'll use this as just the picture we should have for this gardening, where Keith comes in, that's where he's at right now. He's on the moon rototilling the surface so we can't find water, right? Keith's the reason. But the idea of gardening is exactly what it sounds. The moon is being bombarded by objects, and during that process, it mixes the material together, right? And so because it has no atmosphere to protect it from meteors, right? In the Earth, these meteors burn up before they hit the surface. It's very rare for craters to form. On the moon, it happens all the time. And so the material is always being pulverized, destroyed, thrown up into the air, right? And so as we go through the process of craters being formed, right, it comes in, we get this huge explosion, just like we saw with L-Cross, right, the shooting a rocket into the moon. Material flies up. And as the crater formation actually happens, that material is going to fly and float back down onto the surface. But it's also going to mix together. And because we've shot this material up into the air, it's no longer permanently shadowed. So water is going to start evaporating away. And so as this material falls down, any water that was still there is going to end up mixed together with the surrounding rock and debris. And most of the water will have evaporated away. And so this is why we can't find water in that top meter, right? And so models of gardening tell us, as we go into the surface, right? So if the surface is up here at the top, and on the x-axis tells us time, so how old the crater is, this gives us information about how well gardened this material is, right? How many times did Keith go and rototill the surface? And so what we find is in the top 10 centimeters specifically, it is very, very well gardened. We're not expecting to find basically any ice. As we go further down, maybe another 50 centimeters or so, we're still seeing evidence of reworking where there's likely not to be much ice because most of it evaporated away. And this continues down as we go into a meter or even further down. And so this really limits us in the amount of water we can see. And so combining this with our neutron spectroscopy data, which is only limited to a meter, we start to build a better picture of, okay, we're understanding why we're not finding water as easily as we have other places, right? And so how do I prove to you that gardening is happening, right? How do I prove to you that it happens at the rate that it does? Well, we can look at cosmic rays. Cosmic rays give us information about the history of the moon, and this can give us information about the rate at which gardening happens. So remember at the beginning of the talk, I mentioned cosmic rays will spallate with materials and form these cosmogenic radioactive materials. Excuse me. And this results in atomic changes of the regolith itself, right? And these new isotopes, which are not natural to the moon, give us information about its exposure time. It also, these are unstable particles, and so they decay over time. And by looking at decay products, we can age the rocks themselves. Now, this sounds like a very similar principle to carbon dating, and that's because it is, right? It's the same idea, but instead of looking at carbon, we look at cosmogenic material that we know only forms from cosmic ray interactions, right? And as a fun fact, the technique of carbon dating was actually developed here at UChicago in the 1940s. And we say, okay, I know that cosmic rays are forming these cosmogenic materials. I'm expecting gardening to happen. So what should I see in the data if I were to bring home a whole column of the moon? Well, if gardening is not happening, then what I expect is most cosmic rays hit the surface and interact immediately. So I would expect a lot of cosmogenic material right at the surface, and as it goes deeper and deeper down, less cosmic rays are able to get down there, and so I expect to see less material. But if this gardening process is happening and mixing the material, I would think, oh, there should be a mixture or a constant amount of material depending of how deep Keith rototilling the surface, right? And so we brought back core samples. So here's an image of Alan Bean from Apollo 12 bringing home a core sample. And so what we did was we basically just stuck a pole in the moon and we just hammered it down. And then when we brought it brought up a bunch of material with it, and we were able to bring back about 3 meters depth of material. Now, fun fact, the last man to walk on the moon was Gene Cernan, who's from Chicago. I tried really hard to find a picture of him collecting a core sample, but I couldn't do it. So here's a fun fact. But here's what we see when we looked at these core samples. So these black lines are the model of if there was no gardening happening, right? And so as you can see, as you go into the regolith, it immediately just starts dropping. And then eventually we get to the point where cosmic rays aren't even able to penetrate anymore. And so the number of cosmogenic materials or radioactive materials just plummets. But what we actually see in the data is a roughly constant amount of cosmogenic material as we go deeper and deeper into the moon, right? But by the time we reach roughly 50, 60 centimeters, it starts to decay off. And then by the time we're beyond a meter or so, it fits back perfectly to the model of no gardening, right? And so in this way, cosmic rays have informed us to understand that gardening is happening, and this allows us to understand why we can't find water in the first meter or so, or why it's very difficult, right? And so where is all the water? If these processes are destroying the water, moving it up into the space, and the sun is evaporating it away, I promised you Lake Michigan. So where is it? Well, we put all of this new information together, we form new models, and we say, well, it must be further down, right? Based on our understanding of solar implantation, hydrated impacts, and all of these other things, we still believe there to be Lake Michigan's worth of ice, it's just further down. And so in these images, these come out of a model in which you see at the surface, there's no ice. And as we go deeper down, we start to see ice and moon mixtures until eventually about 5 or so meters down, we start seeing these pure ice deposits. And so now the question is, all right, our models are still telling us it should be there, but neutrons aren't getting us there, and we don't want to blow things up. So how else can we probe further down? And for that, we move into looking at cosmic ray radio emission, right? And so the idea here is cosmic rays come in, they interact with the moon, they produce their neutrons, but if they're high enough energy, one of the byproducts is they produce a strong radio pulse. This radio pulse, because it's happening inside the surface, right, it can propagate downwards and much further than what we can typically get with radar, reflects off an ice layer, and then we can detect this at an orbiter, right? And so very similar to the neutron idea, right, where we had a orbiter that went around the moon and just counted the number of neutrons that leaked out of the surface. With this radio idea, we say, let's just go around the moon and count the number of radio pulses we see coming out of the surface, right? And so this is what my thesis is actually on, is in modeling and developing this idea of how we might be able to use cosmic ray radio emission for detecting ice on the moon. And we're calling this CORALS, or the Cosmic Ray Lunar Sounder. But to understand how this radio emission happens, we need to talk about Cherenkov radiation. Now, I know Keith has talked about this in previous lectures, but I'm just going to quickly recap it in the next few slides. But the basic idea here is that light slows down inside of materials, and because it's slowing down, there's an opportunity for particles to move faster than the speed of light inside that material. When this happens, you get emission of light, which we call Cherenkov light, and it typically peaks in blue light, right? And this only happens if the particle is a charged particle, right? And so here's a video of that particle just going through, and you can see how the atoms around are responding. But we want to look at the radio emission specifically. And what you'll see is the particle, as it moves forward, outpaces the emission from this Cherenkov effect. And because of that, it's forming a cone-like pattern. And so the emission comes out in a cone. So this makes it analogous to a sonic boom, right? And the angle of this cone that this emission is coming out at gives us information about the particle, its charge, how fast it's going, and the material that it's in, right? But this isn't the whole picture, or this isn't what we need to know by itself in order to understand radio, right? Because this is happening in the visible. What does this have to do with radio? And so to answer that question, we have to ask, well, in particle showers, there's not just one particle moving faster than the speed of light. There's billions. And in the lunar regolith, because it's so dense, all of those particles, those billions and billions of particles, are all contained within a small disk about 10 centimeters, right? And so if you have billions and billions of particles, all doing the same thing of producing this Cherenkov emission, what does the end result look like? And for this, we end up with a radio pulse, which we call coherent Cherenkov, right? This is what happens when you look at billions and billions of particles. They coherently add. And what do I mean by coherent addition? Well, remember, light is a wave. And so because of that, they're very easy to work with. We can just add them on top of each other. And you might think, well, where have I seen adding waves together in such a way as we make things bigger? Well, you can think about trampolines, right? And so when you would jump on a trampoline with a friend, sometimes you would time your jumps and hit the trampoline and bounce at the same time, and you'd bounce much higher, right? So you were adding your waves together. But if you happened to be going down as your friend was going up, they kind of stole your jump, right? And you didn't get to jump nearly as high. And so here is a video of, hopefully the sound doesn't come on. Oh, well, never mind. Let's try this. Yeah. So this is actually a video of a world record jump where you see the person in the center, as they're coming down, the people are surrounding him are timing their jumps so that way we are adding waves together and they jump higher and higher and higher. And so we say, okay, how can this be useful for Cherenkov light, or at least specifically for the Ascarian effect? Well, we need things to be timed right? And nature is not going to be kind to us. It rarely gives us things perfectly in time or out of time. Fortunately, we don't often need things to be perfect, we just need them to be good enough, which is exactly what Keith said when he decided I was going to give this lecture. And so, what does this idea do in terms of Cherenkov? Well, if we have billions and billions of particles all emitting Cherenkov emission, and they're releasing a spectrum of light that by themselves peak at blue light. But for radio, which remember is at the low end of the energy spectrum, and so really long wavelengths, and they're all separated by just 10 centimeters randomly thrown in there, those really long wavelengths, it's really easy for them to add up onto each other, right? But if we're talking about the blue Cherenkov light from them individually, that timing needs to be precise to 1 in 65,000th of an inch. That's extremely difficult to do, especially if you're just randomly throwing things in a 10-centimeter disk. And so the end result is the blue light kind of washes away from just things adding together incoherently, but the really long radio waves add together in such a way that they become a very massive radio pulse, right? And so that's what the Ascarian effect is, and we could look at what these types of emissions look like and how we can use them on the moon. And so here is a simulation of a cosmic ray coming in, and as you'll see when I play it in a second, you'll see the cone-like pattern that, right, because the Ascarian comes out at the same Cherenkov cone, but instead of being blue, it's radio. And so it comes in, you see the cone right there, and there's a bedrock layer, and so it reflects off that bedrock layer. It comes out of the surface, and then you can detect that with your antenna on some orbiter. And you might say, this is a neat idea, but how do I use it to actually tell if I'm looking at ice, right? And so we can just very easily look at simulations where we say, well, here is my Cherenkov cone. It reflects off of that ice layer at the bottom, and I'm detecting the field at that red point. And we see over here, we saw this massive impulse, right? Which is what we saw, or what we might expect. And then we say, all right, so that's the ice situation. Let's do the same simulation, but instead replace that ice layer with rock, right? And so everything about it is the same. We get a reflection, it refracts through, it goes up, we detect it at our detector, and from this point of view, it looks identical, right? So at this point, you might be saying, so we can't actually tell the difference, this is useless, right? But the key difference comes from zooming in on that main pulse. And so for that, let's redo the simulation just looking at the main pulse itself. And so what we see is that rock and ice actually give opposite polarity signals, right? And so from this, we have a natural way of telling the difference between ice and rock. And that's not the only place that this, or only information that we can gain from these radio pulses. So for instance, some of the energy, when it hits that layer of ice or rock or whatever it is, some of the energy will continue propagating down, and it will do a secondary reflection off the bottom of it. And so we have the opportunity to see two pulses. And in that case, the time difference can give us information about the thickness of the material itself. So now we have ways of distinguishing ice and rock, and we have ways of telling the thickness of the material, right? And so we can actually see, are we looking at a Lake Michigan worth of ice? Not just, well, it looks like there's ice there. This technique is also useful for other geological features such as lava tubes, right? So lava tubes are regions where you had underground lava flow, and over time, that lava eventually drained away, and it left behind a cave. Currently, we find them just by looking for craters that collapsed into them. And we're very interested in trying to map lava tubes over the surface because if we want to further human space exploration, then we have to have a human presence on the moon. But to do that, we have to answer the problem of the moon's environment is very high in radiation, right? It doesn't have an atmosphere or a magnetic field to protect us. And so we say, all right, well, the easiest thing to do would be use the moon itself as our shield if we could find a cave. And so lava tubes provide this natural safe place to protect us from radiation. We just don't know where they're at. But if we're staring at the moon, they're going to give us a very similar pulse to ice, right? But the difference is these lava tubes aren't expected to be at the permanently shadowed regions, so they give us a unique signature at other places across the moon, right? And so you might say, all right, what does this actually look like? So here's an image of what we are, of what we picture this instrument might look like with those antennas up at the top. And similar to the neutron idea, we just fly around the moon and we just listen or look for radio pulses leaking from the surface. In a 2-year mission, we're going to get thousands and thousands of radio pulses. And so with that, we can start to look at what the structure of the moon, of the subsurface of the moon looks like across its surface. And not only that, remember the neutron idea was only able to probe 1 meter. This is able to probe down to 20 meters. So we're actually able to increase our probing depth by a factor of 20, right? Now the Lunar Reconnaissance Orbiter, or the neutron spectrometer, has been operating for 17 years. If we could get a similar live time with an instrument like this, we'd paint the entire moon in these radio emissions, very much allowing us to get a detailed map of the subsurface. But, like I said, this is just a prototype. We're trying to figure out whether this type of idea would work. And so in order to do that, we have to work on what our lens is. For the neutrons, we have a very specific lens for viewing them, and for radio waves, we use antennas as our lens, right? And so here's an image of us prototyping the antenna we would like to use. And if it looks real wonky, that's because it is, right? These antennas are actually printed onto a flexible material because you can't just put a big clunky antenna on a rocket because when it blasts off, it's just going to fly off, right? So we need some way of compacting it, and then once it gets into orbit, it can deploy outwards. And so that's why our antenna is printed onto what looks like a very flexible material, and it will actually roll down, and then once it's in orbit, a central rod will deploy it outwards. And then you can see at the end of it, we're also prototyping the electronics for how we would then connect this antenna to the rest of the instrument itself. And these electronics are actually being prototyped and developed here at the University of Chicago. And so here is an image of us testing out this initial prototype at the University of Hawaii. And we learned a lot from this. We learned that our electronics weren't really working. And so we came back and we said, well, let's redo it, like version 2. Nothing ever works the first time you do it. And so here are some images of us doing a new prototype test here at the University of Chicago, specifically making sure that the electronics work. And we're building up to having a new version of this antenna that we're hoping to test out later this year. Right, and so all of this has been what I've been working on as part of my thesis. And as we come here to the end, right, this idea of trying to use cosmic rays is ubiquitous across many different fields. And the moon provides us a very rare opportunity of a nearby but very different environment for exploring how cosmic rays interact with its surface and evolve it, right? It also provides us rare opportunities for searching for resources that are useful to us and understanding the extreme environments in which they can exist, right? And whether that's by blowing it up, using neutron spectrometers, and then we learn new things, right? That, oh, part of the reason we can't see it is Keith is ruining our lives, right? He's coming along and with his John Deere and just digging up all the ice. And so to get around Keith, we say, all right, let's change our lens. Let's look at radio emission, right? And so all of this helps us to build new ways of solving problems because we live in the sea of cosmic rays and we just have to change our lens and we can learn new things about the universe itself. So thank you.